Well, good afternoon, everyone. Is this on? You can hear it. Is it going? Sounds like it could. Okay. All right. Thank you. Yes. Good afternoon. I'm Bill Hubbard. I'd like to welcome everyone on behalf of the Lunar and Planetary Laboratory and the Department of Planetary Sciences. We're here today for the presentation of the Leon and Pauline Blitzer Award for Excellence in the Teaching of Physics and Related Sciences. I'm a former director of the laboratory and head of the department, and I'm standing in for our current director and head, Tim Swindle, who had to be out of town on official business today. I had the pleasure of knowing Leon back 45 years ago when he was working with Gerard Kuiper to establish the Department of Planetary Sciences. And the idea was that the department would be the teaching arm of LPL and that it would perform its function at the same level of excellence as that achieved by LPL research. And so we're very proud to have one of our faculty receive the Blitzer Award because it's evidence that we're succeeding in meeting that lofty goal. For our further remarks, I'd like to introduce Joaquin Ruiz, who is our dean.
And let me also welcome everybody here today. Obviously, Leon and Pauline Blitzer made a difference to many, and you have everybody in this room is here because of them, either because they knew them, or because they knew of them, or because they were touched by whatever they did. And what Professor Blitzer did, of course, was bring the Department of Physics at the University of Arizona to the 20th century at that point, where research was important. And he recognized, I think in many ways, what many of us don't really say, but intuitively recognize, and that is that the role of universities like ours, the role of universities that are state-funded in some way or another, is to give undergraduate students the opportunity to get engaged in research and what that research brings to their education. That's the big difference between us and liberal art colleges. It's not that one is necessarily better than the other. I actually think what's better, but it's the fact that we bring to the education of the students the creation of knowledge and not just the transmittal of knowledge. They are involved in that creation. And Professor Blitzer understood that because he understood the power of doing research, and he understood the importance of educating with the power of doing that research. So thanks to the Blitzer family, Mimi and Charles sitting here, and their friends, we now have, this is the 12th event in which we're honoring somebody from the University of Arizona with a Blitzer name, and that somebody represents what the Blitzer family was all about. And that is very powerful research and as powerful education. So today it is my pleasure to introduce Joe Giacalone, who is just that. He actually is Mr. Sun. He educates everybody in this campus about how the sun operates. He teaches at all levels. He is highly regarded in his field, and he is highly regarded by his students. And instead of going through the details that are obvious, that you can read in that document there, I don't want to take any more of Joe's time, and let me introduce, he's going to talk about how the sun works and how he screws everything up. Is that sort of the way that goes? Yeah. Joe, please welcome Joe Giacalone. Oh, Randy, sorry, I screwed up. I always screw up. Where's Randy? Randy. Well, he's sort of slouching in the back. Yeah.
I thought I got off.
Well, no. I thought you went after he gave his talk, so I apologize.
Well, as I say, I thought I was off. Well, it's a real honor for me to be here for two reasons. My PhD advisor, when I was a graduate student, wrote a book with Leon Blitzer back in the 1940s, maybe 1950s. And when I came here, Leon was very careful to be very friendly with me because I didn't know as many people here as I do now. And so he was a good friend, and I really appreciated knowing him. Joe Giacalone, our current awardee, is a member of the group that I formed here after I came. He came here in '93, was it, Joe? It's 24 years ago as a research associate. He was hired to work with the Ulysses space mission, and Joe's moved up through the ranks and has been a full professor. How long, Joe? A couple years? 4 or 5 years, yeah. He got his PhD from the University of Kansas, spent time at the Queen Mary College in London, and has had many awards in addition to this one. He's had an NSF, National Science Foundation Early Career Award, served on many, many scientific communities. But best of all, he's recognized in this department as one of our excellent teachers at both the undergraduate and the graduate level. And that's a good part of what this award is all about. Joe.
Is this on? Green light says it's on. But it doesn't seem, I can't hear the echo. Can people hear me back there? How can you
This
tell?
one is on.
Oh, I think it's on. Okay. Maybe I have it too low. I'll raise it a little bit. Okay, well, thank you, Randy, Joaquin, Bill, for those introductions. I'm very honored to receive this. Yes, Bill. I think that's after. Yeah. Huh? Right. Oh, wait. The real winner was the following. That's right. That's right.
I probably got my brain scrambled because Joaquin scrambled some. And so the next thing on this
No, I think it's after, is it not? Right? Charles? It's
is award presentation by Jacob, Malik, and Eric Blitzer. So these are the current generation of
okay.
Blitzers.
Hi. Hello? Can you hear me? Great. I mean, it is a great honor to be presenting this plaque and the accompanying check to Dr. Giacalone. I am here from out of town. I don't make it here every year, and it's a real honor, and this is the best way I could imagine to honor the generosity of spirit and commitment to education that my grandparents were all about. And
thanks for rolling it back so I can get some public speaking practice. All I really have to say is that in years past, I've talked a lot about my grandfather, and it's a great opportunity to learn about him. But also, this award is in my grandmother's name, too. And the saying goes, behind every great man, there's an even greater woman. And if we had more time, I could tell a funny story where she was disciplined for for hanging out with him when he did research in the observatory over there. But here we go with the speaker.
Thank you. Great. Thank you very much. I'm very honored to receive this award. Thank you very much. I appreciate it. I'd like to say I wish I would have known Professor Blitzer, but a little bit before my time here. But following along with what Joaquin was saying about research prowess and teaching prowess, I do take both of those very, very seriously. I'm in this business because I like to solve problems. I'm a curious person that, yes. I don't, it's working. I gotta move it up. I can actually maybe swallow it. Maybe that'll help. I don't know. Can you still hear me? I'll just try speaking a little louder. Is that better? Okay. So yeah, I'm basically a curious person. I find science a endeavor of trying to solve puzzles presented to us by nature, and that's the way I have been for a very long time. You'll see in that program that I did do a stint of playing baseball at BYU. I was on the BYU baseball team my freshman year. Thankfully, I got very poor grades that first year because they wouldn't let me back in because of grades. And so I went back to doing science and mathematics that I was good. I was actually good at that, okay? I wasn't a bad baseball player either, but doing both was very difficult. But I do take my research very I love my research. But I also, teaching, I get a great deal of pleasure from engaging with the students. And I think that's the spirit of this award. And the teaching is not just something that I enjoy to do, it's also something that really benefits. It is a marrying of the research as well, because I learn a lot from teaching. I learn things when I teach classes. I do teach at all levels, and every time I teach, I learn something new, and that just adds to my research. So anyways, thank you very much for the award. Okay, so let's talk about the sun. So this is actually one of my favorite pictures of the sun. It's a picture that you can't just take one snapshot of. It's a composite picture. Okay, you would never be able to see the sun and see the corona at the same time in the same image with the same instrument. Okay, so this is one instrument, and then the corona is a different instrument. I like to start with a picture of a solar storm. This is the sun in X-rays. You can't see X-rays from the ground. You got to go into space. So this is from an instrument that we have in space from SOHO. SOHO happened to take a snapshot of the sun that day and saw this massive flare off to the side. This is the largest flare on record since NOAA began recording them in the 1970s. Since these are X-rays, the emissions that you're seeing there are produced by extremely hot gas in the sun's outer atmosphere. Much hotter than what you see, than the surface of the sun. The surface of the sun is, well, to quote a physics number, it's about 5,800 Kelvin, okay, or 5,800 degrees Celsius or something like that. But that is actually quite cold compared to the gas that's producing that image. That is produced by million-degree gas. And this one is a extremely massive energy release that occurred. Okay, very brief flash of light. That's what a flare is, in fact. A flare is a brief flash of X-rays. And it's associated with the reconfiguring of magnetic fields in the solar atmosphere. You have to, there's very strong magnetic fields in the solar atmosphere. And those magnetic fields, when you reconfigure them, they have a lot of energy stored up inside of them. And when you turn that energy into electric fields, you get massive energy release. And it turns out that the energy release for that flare was estimated, and you can do the calculation. It's about 100 times greater than the energy that was deposited to Earth's surface by the asteroid that led to the extinction of the dinosaurs. So there's more energy in that flare than that asteroid, which thankfully is not going to hit us anytime. Hopefully, it doesn't hit us anytime soon. These things happen pretty commonly. Maybe not this big, but you have very large flares that occur on the sun whenever there's a large magnetic active region. This particular flare, actually, earlier, the sun rotates, and so about a few days earlier, about a week earlier, this active region that produced this was right here, and it produced another really big flare. So that was, within a week, you had two massive flares. So it happens unpredictably. That's the problem with the sun. It's unpredictable. Okay, let's talk about the predictive sun. The sun does behave predictably too, okay? In fact, I like showing this image. This is what's called the sun dagger. It is on Fajada Butte in northern New Mexico, Chaco Canyon, petroglyph. It was discovered back in about 1980, I think, somewhere thereabouts. And the scientists that discovered it noticed that the slivers of light, it's not just a petroglyph, it actually seems to be a calendar, some sort of sundial in some sense. That during the, I could have this wrong, I think at the summer solstice, the light goes right across the middle, and on the winter solstice you have two beams of light that are on the outside, and then on the equinoxes they hit at certain points along here. And so this is the basis for our clocks. The sun is the basis for our clocks. It's got a very predictable cycle. By the way, the sun dagger, this doesn't quite exist in this format anymore. I don't know if anybody knows the story, but Robert Redford did a documentary on the Anasazi Indians, and who constructed this. At least that's the thought that they did. In that documentary, he highlighted their work, but that led to a big flux of tourists to the area to see this. And it's up on a big butte, so you got to hike up this trail to get to it. And when you have thousands of tourists in the arid deserts of the Southwest, and then the monsoonal rains later in the year lead to erosion and all of this sort of stuff, and the settling in the butte led to this thing not existing quite like this anymore. But the petroglyph, of course, still exists. It just doesn't exist in the way that it was designed. The sun's predictable cycles has a number of effects on the Earth. Of course, the reason for the seasons. I like to point out that it does snow in Tucson. That's my mailbox, front yard. I don't know, with global warming, it might not snow too often anymore, but this was about 4 or 5 years ago. There are seasons in Tucson, not just the fact that it snows. There are a lot of people who are new to Tucson don't realize that there are seasons in Tucson. There are. You just have to recognize them, okay? One of them is that when the saguaro cactus blooms. Does anybody know when the saguaro cactus blooms? May. Does anybody know why it blooms in May? Because of the timing of the dropping of their seeds and produce all those red, when birds start pecking at the stuff on the inside and the seeds come out. The timing with the start of the monsoon season, okay, so they can perpetuate themselves. These type of flowers also come out kind of during the monsoon season, usually in August. So the sun, the day-night cycle is caused by the constant sun and Earth's rotation. Seasonal variations. There's also climatic changes on the Earth having to do with the fact that the Earth's orbit around the sun is not constant. Both the eccentricity of the orbit, the amount that it's elliptical, changes. Its tilt on its axis also changes. So all of these things may lead to ice ages or warming periods in the past. But all of this has nothing to do with the varying sun. It's our view of the constant sun. The sun itself does change, though. The sun itself changes. It's best seen in X-rays. It does also change in visible light as well. You can see variations due to visible light. This is X-rays. This is solar minimum. This is a montage of images over about 11 years. 11 years from solar minimum to what's called solar maximum. Okay? And the sun gets very bright in X-rays during solar maximum. It's very dim in solar minimum. These are all images of the solar corona, which, as I said, was very hot. This is another image of the corona. This is an amateur photograph. It's a fantastic picture showing all sorts of little striations that are very likely caused by magnetic fields near the sun. There's also going to be another eclipse here, that's visible in the United States, actually extremely visible, and totality will cross right across the country. Okay, it's August 21st. Which students, by the way, Joaquin and my class were lobbying that we should move, because this is the first day of classes in the fall. We need to move it 1 week later so that they can go see the eclipse. Okay? So I told him I would lobby at today's lecture, because I knew you were going to be present, right? Anyways, August 21st, which happens to be the first day of classes, I guess. I didn't know that till the students pointed that out to me today. And this is the path of totality. The path of totality is right here. And I put the times on here roughly. It's not exact, but Portland, Oregon, roughly is a good place to be. My dad happens to live there, so I think I'll probably head up that way. In the morning, this is local time, and here's the path, okay? And you can look that up. But it's going to be a very exciting time. So it'll be a total eclipse. Here's a movie. This is making an eclipse in space. So in space, where you don't have to worry about the atmosphere causing scattering of light, you could just sort of put your thumb out in front of the sun, or you can build a fancy occulting disk. That's what that is. And you're just looking at the solar corona. Time-lapse photography over several days around Halloween 2003. So these are called the Halloween storms. A really big one's about to happen. And you're going to see all this sort of stuff on the detector, that one. Those are actual particles. Those are the particles I study in my research, the processes that accelerate these particles. Those are actually particles hitting the detector and causing noise on the detector. I can tell you would not have wanted to have been on a spacewalk that day. Okay? Well, low Earth orbit, you're protected because of Earth's magnetic field. But if you were out between here and the moon, and you were doing a spacewalk for whatever reason that you would be doing a spacewalk between here and the moon, that would have been a bad time. The other thing about that image before, I don't know if you saw that bright thing. I don't want to replay it, but you saw that thing going in front. That's actually Mercury. That was the planet Mercury. Everything was adjusted so that the sun was at the center and staying there. You saw the stars moving because the stars move relative to the sun, and then Mercury was moving the opposite direction. Okay, I alluded to the sun's cycle, and I referred to terms like solar maximum and solar minimum. Those refer to the sunspots, number of sunspots. The sunspots have been observed for a long time, but they were really tabulated on a continual basis starting back in Galileo's time. They had been seen before that, but not record keeping quite as meticulous as since Galileo time. Here's a slice of this, and it wasn't recognized actually until the 1700s that the sun goes through a continual cycle. So if you just count the number of sunspots on the sun, and you have to weight it, bigger sunspots get more counts than little sunspots, so it's weighted to the size. But if you do that, just count them up, and you do this versus year, you see this very well-established 11-year pattern. Okay? Sunspots go up and down with a very well-established pattern. And solar maximum is the time where you have lots of sunspots, and solar minimum is when you have few sunspots. And I'm not talking about any individual day. I'm talking about averaged. Interesting fact, the reason why it kind of started a little later, and this wasn't known for a while, is because there were very few sunspots for about 80 years prior to this, 70 years prior to this. This is a period of time known as the Maunder minimum, coinciding, interestingly enough, with the lifespan of Isaac Newton. Isaac Newton apparently didn't know a sunspot. There were 50 sunspots in his life. Okay, he was a theorist anyways. He probably never looked through a telescope. But anyways, so because they had gone away and then they came back, this pattern wasn't seen until later. Okay, does the changing sun affect the Earth? The answer is yes, it does, but it wasn't recognized right away. Richard Carrington, was a solar astronomer in England at the time, was the first to sort of propose that there was a connection between solar storms and the Earth. And there was a very large event that occurred in 1859, I believe it was, called the Carrington event, a huge solar storm that led to aurora that were at very, very low latitudes. It led to currents in the ground. The changing of Earth's magnetic field leads to currents in the ground. At the time, we had telegraph was available. And the ground currents were so strong that they shorted out some of the circuitry in these telegraph stations. So, and in some places, apparently, they were running the telegraph without any power. The currents in the ground were sufficient to run them. So that was the technology at the time, and he made the connection between these aurora, the bright auroral displays at low latitudes, and something that had happened at the sun a few days earlier. Okay? Even though the X-rays comes to Earth in about 8 minutes, that's the light travel time, the storm itself is predominantly a large mass from the sun, something called a coronal mass ejection, that moves out at speeds about 1,000 to 2,000 kilometers per second, and it takes order of a day or so to get to the Earth, or a couple of days, depending on how things go. So that's why these storms occurred later. We're in an age now where we rely extremely heavily on technology. And technology and industry very much cares about solar storms because they affect communications, they affect satellites. I'm going to show an image of an orbital decay thing here in a little bit. You don't want to launch a spacecraft up there that 2 years later is going to suffer too much orbital drag because Earth's atmosphere has gotten a little bit more expanded from solar activity and lose your many $million spacecraft. And by one estimate, I'm not an expert at estimating costs, but one estimate, we're talking trillions of dollars per year during solar maximum in collateral damages caused by solar maximum. So if you're interested in looking at this further, there's a website that discusses all of these different effects. I like to show this slide in pretty much all classes that I talk about this, because I like to talk about some other things. So first of all, geomagnetic storms. So when the sun has a big coronal mass ejection, it goes off into space, and if one is directed towards Earth, and the science of it has to do with the direction. Okay, so when a big chunk of the sun comes off, there's magnetic field that's sort of keeping it confined. This magnetic field is sort of in the form of a giant helix, okay, and it sort of expands out in a big loop. And the direction of that magnetic field, if it happens to be opposite the direction of Earth's magnetic field, it's called a southward pointing coronal mass ejection field, then you get a massive you get a massive geomagnetic storm under those conditions. That can lead to huge ground currents. That can short out. Like there was a very famous one that happened in Canada in 1989. Oil pipeline corrosion, number of different. Primarily, the issue there is the setting of these. Everything's fine-tuned for a flow of fluids through these pipes, and they're set up for long-term use, and so they have to sort of optimize the setting of these pipes. And so they do this with a meter, and if there's lots of ground currents on that day, they'll set it up wrong, and their pipe, instead of lasting for 20 years, will last for 5 years or something like that. So a lot of people care about that. Telecommunication failures, that happens because the Earth's ionosphere, where a lot of these signals have to pass through, are fluctuating like crazy. Satellite damage, you can have single-point upsets when large charged nuclei make their way and hit, especially heavy ones. There's heavy nuclei. It might not be many of them, but they carry a lot of kinetic energy, and they can cause damage. But there's also the orbital decay issue that I'll mention in just a second. And then I like to talk about this. This is actually something I've read. I can't say I've researched it very carefully. But apparently you can go out and buy homing pigeons and enter into a contest where you go somewhere and you set your homing pigeons off, and the ones that get home first, you win. Okay, so it's a big competition, I guess. And so this happens, okay? But apparently during geomagnetic storms, the homing pigeons can become confused, okay? And so that might lead to one team winning over another team. I think it might just be poor sportsmanship, but one might imagine that homing pigeons navigate through Earth's magnetic field, and if you're fluctuating it, it could affect that. Also, there is a correlation with sperm whale strandings. So this is ancient data from the 1800s, but they counted the number of strandings on beaches in England and in Nova Scotia and various places. And they noticed that the strandings of these whales seemed to have a pattern that was consistent with the sunspot cycle. Again, maybe the sperm whales navigate through magnetic fields, and anyways. That's the extent of establishing that correlation. There's also high-energy particles, which I study. You saw some in that image before. I'll talk a little bit about that later. Is there a sun-climate connection? Let me address this one in just a second. But the mammal populations, it turns out, again, the mammal populations of this is called the snowshoe hare. Its population goes up and down, oddly enough, with an 11-year cycle. Okay? Is that a coincidence? Probably, but it's interesting. The way they do it is actually interesting. They had data from pelts, long ago, 1700s, 1800s. They had pelts, and they could just look at the sales of the pelts. But there was they also were getting longer-term records, going back before that, from notches in tree rings, that this particular rabbit likes a certain kind of tree, and when their population is high, you see certain irregularities in the tree rings. And so using the tree rings as a dating tool, they can go back farther. So it's actually kind of an interesting correlation. What's the physics behind that? I don't know. Okay, there were just a couple of effects. This is just a plot of some data. This is not my research. This is just some research I'm aware of, though. This is a plot of what's called the total electron content in Earth's ionosphere, TEC. That's that TEC there. And the units are something like some number that probably doesn't have any meaning, 10 to the 16th per square meter or something like that. But it shows before a large solar storm. This was that Halloween storm, before and after. So there's a very huge difference in the ionospheric electron density as a result of these storms. And these rapid changes can lead to rapid changes in currents on the ground. This is a simulation, not of that event, but of some other very large event that took place, showing the magnitude of the ground current in these circles. Bigger circles mean very large ground currents. Smaller circles are small currents. The colors represent which way it's pointing. And the lines are transmission lines. These lines are current transmission lines. Okay? And so if an event like this happened, there would be massive blackouts that would occur if this big, huge event were to happen now, according to this calculation. Okay? It's not my calculation, but this, according to this calculation. And it could cost anywhere, it could affect hundreds of millions of people. So, governments are aware of this and are concerned by it. Okay? It rose to the level, actually, President Obama mentioned a priority in learning more about this. Okay? So, obviously, public awareness and improvements in forecasting, which is not easy. Forecasting these storms is really at the level of, you see the sun it rotates, thankfully. You see a big, massive magnetic active region on one side. Okay, the whole time it's in front of you, there's a good chance that something can happen. But predicting whether you're going to have a big geomagnetic storm, the orientation of that magnetic field is not easy. Okay, so things happen unpredictably. And also, I would also point out that this is from the same article. I've got sources to these articles. Today's world is very interdependent. You have a lot of these, these things that depend on one another. And so breaking one thing of the chain leads to a large cascade to others. Electric power, transportation, emergency services. Maybe government services. Okay, they can go out. Banking, finance, and so hopefully there's not any government people. But anyways, water, so they're all interdependent. So the point is that one of these chains going out can lead to problems elsewhere. So it is a big problem, and that's why it's a concern. I like to show this, the orbital decay problem. I like to do orbital decay as one of the problems in my class. It's atmospheric drag, and it's orbits. It's a great planetary science question. So you got orbits, it's a great physics question. So you have orbits, and then you have atmosphere. And the atmosphere is trying to slow the spacecraft down, so the spacecraft is going down to a lower orbit. But a lower orbit means it's closer to the gravitating body, and so it wants to speed up because as you get closer, it's going to start orbiting faster. Its orbital speed gets faster. But its orbital speed is faster means that atmospheric drag is larger. Okay, the atmospheric drag gets more and more, and you're going down to where the atmosphere is more dense anyways. And so it's kind of a feedback process in a way that the decay is very rapid. So a good example, and during solar maximum, the input of additional energy into Earth's atmosphere causes it to expand. Okay, heats up and expands. And so if you're in a nice comfortable orbit at some point, but then during solar maximum the atmosphere expands out, it'll slow you down. Okay, so this is one example. This is a spacecraft launched by NASA called SAMPEX. It's gone now. It landed back in 2013. I believe it hit the ground. Not the ground, but it hit the Earth. It didn't just burn up in the atmosphere. And this is as a function of year, its orbital altitude above the Earth. And that's this unit here. This is the sunspot cycle during that period. And you'll notice that it was in a relatively nice orbit, but then we had a big solar maximum. And look at that big decrease in its orbit that occurred as a result of atmospheric drag. Then it slowly decayed, but it was settling out for a while. And these spacecraft are put up there without a lot of fuel, so they can't do, they're trying to minimize the cost. So it's all about mass, it wasn't able to do too many corrections, but it lived a little bit longer, but then this next solar maximum killed it and just took off. So this is what I'm talking about. This obviously cost a lot of money. Its prime phase mission, ended before, so this was all sort of icing on the cake for the scientific return, but it's a shame it's not producing data. We're not getting data from it anymore. It's got a more pleasing effect, these big storms. This is actually an aurora that took place in Tucson in 2001, March 30th. This is a picture in my backyard of an aurora. It's not a sunset. If it were a sunset, this would all be over there probably, and you wouldn't see stars. Okay? This was back in the days I still had film, 2001. I didn't have a digital camera. And aurora just don't happen in Tucson very often, right? So when I was outside and I saw the aurora, I was like, oh, okay, I know what this is. I want to get a picture of it. I want to record this. So I had my film camera. I didn't know what the right exposure would be. So I played with a bunch of different exposures. And this was the shortest exposure I used, which I think was like 1 second. Okay, 1 second, the moon, this is the moon, is overexposed. And in 1 second, you can see some stars, but the aurora is massively overexposed. It wasn't curtains, but there were variations. So aurora do happen, and actually in that Carrington event, Carrington was able to, so this was, 1859, the Carrington event, September 2. These are all locations of aurora that took place, reporting of aurora. And you can see even down at the equator where they were seeing aurora. So it just, this was a massive storm. Okay, let's see, how am I doing on time here? Okay. Is there a sun-climate connection? I get that. That's a difficult. Okay, I'll just say right up front. I think that there are changes in the sun at visible wavelengths. Its total brightness varies. Maybe I should jump ahead 2 slides real quick. This is something called the solar constant. It's not a constant, okay, because it varies. But the solar constant you can look up on Google. It is the amount of solar light energy arriving at Earth's orbit. Its number is about 1370 watts per square meter. That's the sun's brightness at 1 AU, okay? For lack of a better way to say it. And you can measure it. There's a bunch of different ways to measure it. You want to go into space. You don't want the atmosphere to cause problems. So you go into space and measure it. These are all different instruments that measure this. It's unfortunate that they give different answers. This one's more like 1372, 1369, 1366. So they're not intercalibrated, okay? They don't give the same answer. But they also all show the same trend, that the sun tends to be a little dimmer during solar minimum and a little brighter during solar maximum. This is averaged over all wavelengths. Okay? The X-rays don't produce much into this total flux. It's mostly visible light. So this is the visible part of the spectrum predominantly. And so the sun is a little bit brighter. It's not a big effect. It's like a 1 or 2%. Or no. It's like 0.1 or 2, 0.2 or 3%, something like that. So it's a very small effect. So going back to this question, I'm sure the atmospheric scientists would all say that variation is too small to account for global warming. Okay, global warming, the fact that the temperature is going up like a hockey stick, laid on its side, going up. The temperature is going up. That's not global warming. That's not caused by the sun. The pumping of greenhouse gases in the atmosphere is the largest effect, and that's what I don't study that, but that's I think that a prudent person would say we should stop doing that. Okay. However, this is an interesting intellectual puzzle here. Is if the sun is brighter or dimmer, what effect does it have on climate? And as I mentioned before, there was a period of time, roughly coinciding with Isaac Newton's life, where there were no sunspots. And it turns out that during that time, there were many ice ages reported. So in this period, the sun was dimmer, a little bit dimmer, less solar energy, which heats up the Earth. And that didn't heat it up as much. Small effect, but a little bit. And this is actually a painting of around that time by a painter painting the River Thames. This is the Thames in London. I lived in London for 2 years. I've never saw the Thames like that, okay, where it's frozen completely over. But this was a mini ice age that was reported during that time. So there is almost certainly an effect of the sun on the climate, okay, but we should still not be pumping greenhouse gases into the atmosphere. Okay, the last topic I have, and I think I have a few minutes to talk about it, is the space radiation part of this problem. And this was a snapshot of all those cosmic rays striking the detector in that one movie I showed before. There's also cosmic, so these are what I would refer to as solar cosmic rays. They are particles accelerated by, actually that coronal mass ejection has a big shock wave that it drives, and it accelerates those particles. That's actually my research. And it's the acceleration of those particles that produce these. These are solar cosmic rays, for lack of a better term. But in addition to that, you have galactic cosmic rays that come from outside our solar system. And they are produced, the bulk of them are produced most likely in supernova explosions. So when a supernova, star goes supernova, it leads to this massive blast wave that goes out. This blast wave is basically an extremely strong and extremely large shock wave, and it accelerates particles as well. It's the acceleration at the shock wave that's the predominant physical effect. And it produces these galactic cosmic rays. And so by knowing the number of supernova remnants and the rate at which they leave our galaxy and so on, you can fit these together, and that seems to be the best explanation for the galactic cosmic rays. So there's galactic cosmic rays. There's also solar cosmic rays. The galactic cosmic rays have a very well-known anti-correlation with the sunspot cycle. Okay, it's very well known. This is one way to measure cosmic rays at Earth is through what are called neutron monitor. We have a number of these neutron detectors. They measure neutrons. Okay, and you see a well-known when the neutrons are high, that means there's more cosmic rays hitting the upper atmosphere. You don't actually see the cosmic rays on the ground because the individual cosmic ray hits the atmosphere, leading to a cascade of particles coming down, and nuclear physics takes over, and you get muons. Muons leave an ionization trail in a cloud chamber. I don't know if anybody's ever seen a cloud chamber before. Cloud chamber, and you see little tracks going through. There's ionization tracks, and then you get neutron monitors can also detect these. So this is a proxy for the cosmic ray flux. So when the number of sunspots, which is the top panel, is low, the number of cosmic rays are high. And when the sunspots are high, the number of cosmic rays are low. And I was commenting before that my laser pointer would go out because it's been 2 years since I used it, is correct. And then it's back. So this is a very well-known cycle. Okay, you might actually notice that there's actually a 22-year cycle on top of that. You see this is a triangle shape. It's peaked. This one's triangle. This one's more flat. This one's kind of a cross between the two, but I think you'd call it a flat top. Actually, Randy and I think Joseph was also involved in this, but Randy primarily did explain that. It has to do with the sun's magnetic polarity and the importance of the way the cosmic rays, outside galactic cosmic rays, drift in the magnetic field. And because of the changing polarity of the sun's magnetic field, between two successive solar minima, the sun's magnetic field changes polarity. And that's what causes that. Okay, a colleague of mine by the name of Dick Maywalt at Caltech did a calculation taking these cosmic rays at Earth and working out what would be the dose equivalent to the human body. Okay? And then he converted this plot to a dose equivalent to the human body if you were in space. And since my laser pointer is not really working that well, I'll just describe this. So that's that cycle. The red curve is that cosmic ray cycle. Okay? High here, this is solar minimum, solar maximum, solar minimum, max, and so on. Oh yeah, thanks, Bill. Except for I have to stand over here now. Okay, but this is converted to a dose equivalent felt by the human body. And it's a calculation involving the flux of cosmic rays, which we know pretty well. And, oh, wow. Boy, all I had to do was say my laser pointer was going out. Maybe you could use a beer, too. I don't know. No, I'm just kidding. I'm only kidding. Okay, so anyway, so this is the dose equivalent in REMS, okay? And forget about the number too much, but this calculation assumed 5 grams per square centimeter of aluminum shielding and so on. So you could go read the paper for the details of the calculation. But the thing I wanted to point out is that this is the current yearly limit for low Earth orbit for NASA's limits. Okay, this is the start time of a 6-month mission. Okay, so if you want to go to Mars, it takes more like 8 months to get there, 8 months to get back, and the surface of Mars doesn't afford you that much more protection because it's a very thin atmosphere, and the cosmic rays can come down more or less to the surface, not unimpeded. The atmosphere does prevent some, but not much. And so you're going to be in space for 12, 15, 18 months. Okay? And so if you go at solar minimum, you're above NASA's limit. There's no doubt you're above NASA's limit. So, okay, how do you fix this problem? Well, NASA can change their limits, I guess. That's an easy solution. That's not going to happen. Okay, so the bottom line is if you just take this, it's probably a showstopper to go during solar maximum. If you go during solar minimum, maybe, or excuse me, solar maximum, This is quite a big drop here if you go during solar maxima. Again, this is one calculation. And we don't do tests on the human body with actual particles, galactic cosmic rays striking the body. So there are a lot of unknowns in this calculation. But according to this calculation, solar minimum might be a good time to go. Excuse me, solar maximum. But, okay, as I was just mentioning before, you can't shield from galactic cosmic rays, by the way. If you put out, we are shielded from cosmic rays because of our great atmosphere. But the equivalent that you'd have to put into space would not be cost effective. You just can't do it. You get to a point of the diminishing return. You just can't create enough shielding in any cost effective way. So it's really not something that can be done. And as I said, you really have to build, if you're going to go to Mars, you have to get underground pretty quickly. Okay, so what about going during solar maximum? Well, if you go during solar maximum, you've got another problem. Okay, so these are lower energy. The thing about solar cosmic rays, don't have quite as high a kinetic energy. So this is a unit of energy, okay? And let me just say, a typical galactic cosmic ray striking Earth's upper atmosphere is at about a giga electron volt. So this is 10 mega electron volts, so about 100 times less. You can kind of see the galactic cosmic ray cycle underneath. There is some galactic cosmic ray floor to this, but it's this hair on top of it. These are the solar cosmic rays. This one is 1,000,000 times the flux, okay? And it's unpredictable. There's no pattern in there other than to say there's more here roughly than over here, but on any given day, you can't predict this. It's a very unpredictable thing. So, but we might be able to shield these. These are a little easier to shield. So, but you'd have to, it wouldn't sound like a very comforting thing to me to say, well, there's a big active region on the sun. There could be one of these events. I'm going to go hide in my shelter for 2 weeks. Doesn't sound that great to me, especially since if it turned out to be a false alarm. And I should also point out these cosmic rays they are relatively directional at the beginning of their event. If you think of one of those events at time. So if I were to blow this up in time and see how their time intensity behavior goes, they start off very intense, but they decay very slowly. And the decay phase, those particles are coming isotropically, all directions. So, you could even have events on the far side of the sun that you don't see that produce all these particles that will eventually sort of work their way to you. They'll be a lower in flux, but they could be there. Thankfully, there was a huge solar particle event that took place, thankfully, right between 2 Apollo moon landings. Landing 16 and 17, that's this vertical line here. The solid line's a sunspot cycle. These are these big particle events, and notice how one of these really big ones, it's an intensity, it's a proton fluence, it's a total intensity. Notice how it's right between Apollo 16 and 17. Okay? It's a good thing it happened between them. If it happened during there, those astronauts would have been very sick. Maybe died. Okay? Just to say a few things. When's the best time to go to Mars? Probably best is not to go. Breakthroughs may come in genetics, looking for people who, this is not an easy thing to do. You can't test people. You don't want to radiate people with cosmic rays, but perhaps some people are more, can handle radiation better than others. I don't know. So there's people working on that front as well. If you go during solar maximum, might be the better option because the galactic cosmic rays are way down, but then you got to worry about the solar energetic particles. Solar minimum is probably riskier, too many galactic cosmic rays. And also, these big, huge flares can occur even during solar minimum. The big flares are often at sort of the declining phase of the cycle. So I have just a couple more slides. I do want to say real briefly that I'm interested. This is very much close to my research. So my research, just to have 2 slides related to this, I'm primarily a theorist and a numerical modeler. I model these events. I try to understand the basic physics that lead to their acceleration. Here's an example. This is at what's called an energy spectrum, the distribution of the intensity of particles with energy at Earth. So we have spacecraft at Earth that measure these particles. This is an example from one of the simulations I've done. I simulated, in this particular case, this Halloween event, the really big one. And I also just want to point out that this current solar cycle actually has very few large events compared to previous solar cycles. So if you just if you go back the previous 2 solar cycles and you just start adding up every time a big solar proton event happens, and you just add up how many particles you saw. And you add them up versus time from the beginning of the sunspot cycle. That's what this is, day of solar cycle. All the way across should be something like 11 years. And the integrated amount is really just a fancy word for the total number that we're counting, okay? And cycle 23 was the previous solar cycle. So I don't have the years on there, but I think ending in like 2009, 2010, something like that. I don't know. This one, anyways, there was a large number of them. And then prior to that, 11 years prior to that, there was a fairly large number. But look at the cycle that we're in right now. Very, very few. Okay? Very, very few. I presented a paper at the American Geophysical Union meeting just recently that basically said that the most probable reason for this has to do with the fact that the sun's magnetic field is also weaker. And that's been observed. The field is actually weaker. And what that does is it means the weaker magnetic field slows down the acceleration of these particles. They can't be accelerated quite as rapidly. So my last 2 slides, as I'm finished right now, are to show a picture I take. I like taking pictures of a sunset. This is out my front door. There's a lone saguaro off in the distance. And it's a nice sunset. It produces beautiful sunsets here, but it's actually a very feisty and unpredictable neighbor, that sun of ours. And it would not be, if you're an astronaut, you would know about the sun. Okay? And I'm not talking about just the fact that it's bright. Okay? You obviously don't want to look at it, but solar storms and things like that will cause you problems. Okay? And then this is my final picture. This is just one of my favorite pictures of the sun. I believe this was actually the Kuwait. It was in Kuwait back when we liberated Kuwait, and this is a soldier there, and they took a nice picture holding the sun. It's one of my favorites. You can look at people holding the sun images. Just Google it, and you'll find billions like this. So that's it. So thank you very much.
I think we're going to have the opportunity now to ask some questions. I'm sure there will be a number of them. And Bert has got a microphone, so everybody will be able to hear your question better if you will try to hand it to you.
Without sounding too dumb, my impression is that you're saying that there are specific health effects for human beings. Could you go into that in some detail?
Yeah, first of all, it's basically receiving a massive radiation dose. So it's anytime you have that, that's all sorts of. If your blood-forming organs receive a massive radiation dose, you can have all sorts of effects. Just ask the scientists that were building the atomic bomb. Okay, there were a few that had that issue. So that's the predominant health effect. There could be long-term effects. The astronauts, for example, are known to have cataracts, a higher incidence of cataracts. But if you're going to Mars, those health effects would probably, I don't know that they kill you on the spot, but there's a good chance you come back dead without proper health care. And the thing about the radiation dosage is it's cumulative. Okay, it's not like you just treat it and it goes away. The number of sunburns you've had in your lifetime is a critical issue. It just keeps adding up, and so even though you might get some medical attention, if you're constantly being bombarded by the radiation, the human body doesn't like that. Basically, these particles come in and they hit your DNA and break it up. That's basically what it is. Yes.
I can just comment on that because I did work on this in the military. At 200 rems, you have serious health issues that you can feel. When you get up around 400, you're very, very ill. You get up around 600, you're going to die pretty quick.
Yeah. So I'm assuming all of the different things of being sick, vomiting, and all of this sort of stuff. Yeah. And actually, I don't know. I had the RAM equivalent in that plot before, up there. But it's a cumulative. These are not. This is the galactic cosmic rays that are always sitting there. So you're always getting this. It's not like you got a burst and it's gone. So the cumulative effect is the one. So you might not die, but you might not die instantly from this. But the accumulation, that's why NASA has these limits. That accumulation is what's going to. And so, yeah, I don't know. You come back to Earth and, the next year you die of cancer or something like that. Okay? Yes? Oh.
At the Earth and Science Museum on Mars, and it was teaching children about what. I'm sorry. They were teaching children about Mars, and they had a simulated. The people were there for a period of time, and they said it would be probably in 2030 or 40 that we would be in Mars. Are they aware of your research and what you've just said today? Just wondering.
My colleague here, Randy Giacalone, served on a committee that I think was commissioned by NASA. Is that correct? Yeah. And they wrote a report basically pointing out that it's probably a showstopper. So they are aware of this. Well, that's one interpretation. But I think we will go to Mars. I think there's too much momentum heading that way. We will go there. We're explorers. Humans are explorers. I mean, am I going to go? No, I'm not going. But there will be people that will go, and I think NASA will do their best to mitigate these effects the best they can. They're aware of them. There are instruments. There's an instrument on Lunar Reconnaissance Orbiter. There's a experiment on there which is meant to try to mimic human flesh. It's called Crater, oddly enough, Crater, but it has nothing to do with lunar craters. But it's an instrument that measures cosmic rays going in and their stopping power of this gel. And so they're studying this problem. And they're studying at it from the genetic angle as well. I do believe, irrespective of that, there's people that really want to go to Mars. And Elon Musk, he wants to go there. I think that we will go. We will go. I don't know in my lifetime. I think it's a little ambitious to think we might be going by 2030. That seems a little early to me. I could easily see 2030 come around. Hopefully I'm still around. And we still haven't put foot on Mars. But I think it'll happen. It'll happen. Yes, and then, I don't know, maybe Phil's the one closer and then you're second.
So those 7 planets were recently found in the TRAPPIST-1 system, right? They're supposed to be in a habitable zone, but it's around an M-star, right? And M-stars are what, 100 or 1,000 times more magnetically active than the sun.
Yeah.
Are they also likely to have large mass ejections and things like this? And so
absolutely.
Calling it a habitable zone may not be exactly what you think.
That's a very good point, right. That's right. Lots of solar storms and, cosmic rays striking. Well, if they have really thick atmospheres, these cosmic rays don't make it to the ground, so that's good. But like Mars, for example, thin atmosphere, the ground is sterile. Maybe cosmic rays have something to do with that.
I'd like to bring this back to Earth travel and following the question of the gentleman up there. I seem to remember in the last solar maximum there was a lot of concern about frequent airline passengers and pilots, and I think you had a little comment up there.
Yeah.
Are you aware of any research that's been done on the health of people who were frequent travelers?
I am aware of I can't recall directly, but I would be stunned if there wasn't. Okay, almost certainly there is research being done on this. I'm aware of a pamphlet, though, that goes, or maybe it's more than just a pamphlet, it's actually some material, that they hand out to flight crew that discuss these risks associated with the radiation dosage. There's other risks associated with flying. There is the dose that they get, but again, these are flying in our atmosphere, and yes, there is an increased radiation higher up, but they're still somewhat protected by our atmosphere. But they do get some, okay? The predominant worry for the airlines is really positioning and GPS and communications during a solar storm. That's a big issue because it costs a lot of money to fly, say, from Chicago to Beijing, and you want to take the most economical route possible, and but I've read a little pamphlet that they handed out regarding the radiation risks, and I'm sure there's research, but I just can't think of papers that are out on that right now.
Do you know if the solar activities are associated with the global electric circuit?
I'm sorry, could you say that one more time? I'm sorry.
Do you know if the solar storms or any activities are associated with the global electric circuit?
Are you asking, are there any power outages that have occurred recently? Is that or are you talking about the magnetosphere as a whole and its
No, so there's so under the fair weather, there's a global electric circuit from the ionosphere to the Earth's surface.
Yes.
So I was just wondering if there's any relationship between the two.
Yes, these currents, I went through it a little quickly, but the ionosphere, where that electron density changes quite a bit during a storm, that's all coupled to these currents that we're talking about. It's the ionospheric currents.
So you're saying the potential at the ionosphere is changing?
Yeah, I like to think of it. Well, first of all, okay, let's stick with the observations. I'm a true theorist. Let's stick with the observations. The observations are that the electron density gets very high after a solar storm, and that's in the ionosphere. The ionosphere is the part of the atmosphere where there's a lot of ionized particles and a lot of free-flowing electrons. And those are the ones that carry these currents. Okay? And so they get very high right after a storm. Okay? But I like to think of the ground currents caused by variations in Earth's magnetic field. So if you take a magnetic field and you change it, that induces a current. And those are the currents. But it's coupled. They're all coupled. The ionosphere carries the magnetic fields around with these flows. So the ionosphere is moving around, the magnetic field has to move with that. And then they're coupled to the ground, producing ground currents. That's the way that process works. Does that answer the question?
But are they kind of related? Is there a relationship? Like you have a solar storm and then the currents burst, like the current burst?
Yeah.
Is there
they're related in that sense. But it's not like if there's no storm, we're not coupled into the sun or the solar wind or anything like that pre-storm. It happens as a result of variations, rapid variations. So the sun produces a big event and it goes by you, and then you get these variations. But it doesn't exist all the time. Is that kind of the question we're talking about here? It is related. It's related to the solar storm, yeah.
Thank you.
Yeah.
Thank you. It's Scientific American article by Gene Parker. Can you? I forgot the year and the issue. You may have it.
Right there, March 2006. The March 2006 Scientific American article. There was an article written by Gene Parker, who is a space physicist like us. And Gene's he was on that committee, Randy's radiation dosage committee. Gene Parker is, in my view, should probably have the Nobel Prize, okay, as a space physicist. He did a lot of fantastic work at the University of Chicago. Later in his career, he got latched onto this problem. I think this paper resulted from that committee, his version of that, right? Did he write this paper shortly after your committee?
The story is that NASA didn't want us to publish that because they wanted to go to Mars. And Parker was on the committee, and he got very angry and wrote the Scientific American.
There you have that. That is the whole truth now. Yeah. But this is an excellent article. He goes through all of the issues on here and talks about what would happen, the issue of the health effects. He goes through that. The worst place to be, by the way, for radiation effects is actually inside of Earth's radiation belts. You definitely don't want to be there. The radiation dose is huge because Earth has these two big belts around them. These are radiation belts that were discovered by James Van Allen, called the Van Allen belts. Yeah. Right. Yeah. That's right.
Well, first, thank very much. I think my father would have adored this because he studied orbital perturbations. That was something he loved, and he was pretty adamant that he didn't believe that man needed to go into space, especially Mars, which he told me quite a few times. But this is a naive question. So if there's a massive solar storm that you identify or a flare, how much time do you have to respond here on Earth if you know this happened?
Okay.
We need to protect whatever electrical system.
Yeah, there's various levels to that question. So if it's a coronal mass ejection, you can look at the sun and you can see the coronal mass ejection back at the sun. You can see it in the corona images, those corona images I show you can see it. And if it's what's called a halo CME, it's coming right at you, and so it forms a halo around the sun. So you know it's coming right at you, and those are the most dangerous. And you can estimate the speed of these just by taking subsequent solar images when it's still close to the sun. So you can estimate the speed. And it's of the order of a day or two, depending on its speed, of course. But it's of the order of a day. So
we have people monitoring this all the time?
yes, absolutely. Yeah, spaceweather.com. You can go in there and get the current solar wind speed. It's like a weather page. They give you the local solar weather, right? Then there's the energetic particle part of this. So if you're an astronaut, you're worried about that. The energetic particles that I showed that would be dangerous to astronauts coming from the sun, okay, those are moving. The highest energy ones are a fraction of the speed of light. Electrons are faster, but they're much lower in number. But the protons, those are predominantly protons, they're moving at a fraction of the speed of light. And they also, when they're moving out here, they scatter in the magnetic field between here, and so they kind of go back and forth to get to you. So the peak intensity is usually several hours after, okay, maybe 10 hours or something like that after. And then it goes back down, and then the actual CME comes by, and you get another little burst, which is primarily at lower energies, not quite as damaging, but so hours. And then there's X-rays. X-rays are probably not going to affect you too much. These X-rays are still pretty low in intensity, but a really high flare, very large X-ray, if you're around one of these massive, exoplanets with these very magnetically active stars, maybe they have X-ray flares that are so intense that they could actually cause problems. Those come out at the speed of light. That's 8 minutes for us. So there's a variety of answers to that question. Yeah. Okay. Is that how that works? I march and present at the same time? Or I have like a sandwich board on me?
Well, let's thank Joe once more.
Thank you. Thank you all. Thank you very much.